Welcome to the last segment of this course where we will be looking at the solution of ordinary differential equations. Overall, this will be done in two parts, with the first part focusing on initial value problems and the second part focusing on boundary value problems. The related MATLAB commands for initial value problems, namely ODE 45, and for boundary value problems, namely BVP init and BVP 4C, were introduced to you earlier. We can continue to make use of them to solve problems that are of engineering interest. In the lectures related to initial value problems and boundary value problems, what I'll be covering are the concepts and principles behind the MATLAB codes that I talked about earlier. In terms of assessment for this part of the course, for initial value problems, the emphasis will be on problem solving using ODE 45 or ODE 15S commands. You will not be asked to derive any expressions. You just have to be able to solve problems that engineers have to deal with. You will see those type of problems in the tutorials and assignments given to you. For the boundary value problems, in addition to be able to solve problems of engineering interest using BVP init and BVP 4C, you will also be assessed on your ability to set up the equations that need to be solved. So for your assessments, plan accordingly. The principles are very important so that we do not treat ODE 45 or BVP 4C as mere black box MATLAB commands. As learners, it is important for us to know what lies underneath them. So pay particular attention to the concepts and principles behind the expressions that we derive in these lectures. As you will see, we invoke only two things. One is the Taylor series expansion. I alluded to the importance of Taylor series expansion right at the beginning of the course. The other thing that we will focus on is finite difference approximations that were introduced to you when we looked at the topic of numerical differentiation. So with all these in mind, let's step forward. So now let's look at what linear and nonlinear ODEs are. As we know, we can solve linear ODEs by hand, analytically, and nonlinear ODEs will involve the use of computers. And many systems are represented by nonlinear ODEs. Therefore, we have to make use of a tool like MATLAB, etc. to be able to solve it. Our approach to identifying linear and nonlinear ODEs is based on a very simple idea that we will define the easiest of them. That means we will define what linear ODEs are. And once we know what a linear ODE is, then anything that is not a linear ODE becomes a nonlinear ODE. So a linear ODE has two characteristics. The first characteristic is that all the derivatives will appear in linear form. For example, you can have terms like d2y by dx squared, where y is the dependent variable and x is the independent variable. This is okay because this is the simple second order derivative. You can have terms like dy by dt, where t is the independent variable and y is the dependent variable. You can have terms like d4y by d psi 4. Psi is the independent variable and y is the dependent variable. This is just the fourth derivative. So there is nothing non-linear about any of these. But if you have something like dy by dt the whole squared as a term appearing in your ODE, that would violate the first principle because the derivative appears in a quadratic form here. So quadratic is non-linear. So if this dy by dt has any other power than 1, that would make it a non-linear term. So if ODE has this as one of the terms, that would become a non-linear ODE. The second attribute of a linear ODE is that its coefficients should either be constant or should be a function of the independent variable only. If any coefficient depends on the dependent variable, then that ODE becomes a nonlinear ODE. For example, if I had a term like y dy by dt, here what happens is the first derivative of the dependent variable multiplies with the dependent variable itself. So the coefficient of dy by dt is y, and y happens to be the dependent variable, and therefore the coefficient y depends on the dependent variable. That would make it nonlinear. Now, I've also made one more statement here saying if the coefficients are functions of the independent variable, then it remains a linear ODE, but we would call it a variable coefficient linear ODE. That means instead of y dy by dt, let's say I had t squared dy by dt as one of the terms. So this is the first derivative involving the dependent variable y. So this is okay. Now the coefficient of that is t squared. And t squared has nothing to do with the dependent variable. T is the independent variable. And if the coefficient happens to be a function of the independent variable, it still keeps the ODE as a linear ODE. That's how people have defined it. However, since as we progress in time, this t will keep changing, the coefficient becomes a variable coefficient 1. It is not going to be a constant coefficient. So we have linear ODEs where all the coefficients are constant. Then we have linear ODEs where the coefficients can be variable with respect to the independent variable. So that would still be a linear ODE. Anything that does not fall into these two categories, that ODE will be deemed as a nonlinear ODE. Let's look at a few examples. If you take this first ODE, y is the dependent variable, t is the independent variable, and we are interested to find out how y changes with time, how the dependent variable changes as a function of the independent variable. So that's what we are interested in solving. So dy by dt is a first order derivative. The coefficient is 1, so that's fine. Y is the dependent variable. Its coefficient is alpha, which is a constant, no problem. The right hand side is a forcing function f, which is a function of the independent variable t. So each term there is linear and the coefficients are all constants. Therefore, we call it linear constant coefficient first order ODE. The order of the ODE is determined by the highest derivative occurring in that. Now, instead of dy by dt, let's say the first term was d2y by dt squared, then this would still be linear constant coefficient, but it would be called the second order ODE because the highest derivative is a second order derivative. Now, if you come to the second ODE given there, this is linear as we saw in example 1. This is no problem. The forcing function is a function of the independent variable. And if you look at the coefficient of y, the coefficient of y is some constant alpha multiplied by the independent variable t. So this coefficient alpha t for y does not make it non-linear. So this would be linear first order ODE because the highest power is first derivative. But since the coefficient of y depends on the independent variable t, the coefficient will be a variable coefficient 1. Therefore, this second ODE is linear variable coefficient first order ODE. Now, instead of this second term being alpha ty, it was alpha e to the power of y times y. The coefficient of y is alpha e to the power of y. Alpha is a constant, so that poses no problems. But e to the power of y involves the dependent variable. If the coefficient is a function of the dependent variable, then that would become a nonlinear ODE. So if the second term was alpha e to the power of y times y, or even alpha y times y, then this ODE would have become a nonlinear ODE. Now this ODE is clearly nonlinear because you have this term. The coefficient of dy by dt is the dependent variable y. The moment you see dependent variable terms multiplying each other in the ODE, that would render it to be a nonlinear ODE. It still is a first order ODE because the highest derivative is the first derivative. So this term is linear, this term is linear, this term is what that induces nonlinearity in the system. The next equation again is a first order ODE because the highest derivative is dy by dt. But what you see here is dy by dt appearing as dy by dt the whole square. So it is like dy by dt times dy by dt, and the coefficient of dy by dt is dy by dt here in this expression. So you can write this as this, the product of dy by dt with itself. And you can say, well, the term is dy by dt, its coefficient is dy by dt. And since dy by dt involves y, then this term is going to be nonlinear. So this is the term that induces nonlinearity. If you come to this ODE, it's a second order ODE because the highest derivative is the second derivative. If you look at the coefficients of the different terms, right? So this is a constant term, right? Because the system parameters H, P, L, and K are constants. Therefore, H, P, L squared by K is a constant. Therefore, this is a linear term. No problem. When you come to this term, this is the first derivative of theta with respect to psi. So theta is the dependent variable and psi is the independent variable. So this d theta by d psi is okay. But if you look at its coefficient is a function of psi, which is the independent variable. That's no problem. However, this will be linear, but will be called a variable coefficient linear ODE because this term is going to change with respect to psi. As psi, the independent variable changes, dA by d psi will turn to a different value. Therefore, the coefficient will be variable. The same argument for this term as well. The second derivative gets multiplied by a term that is a function of the independent variable psi. So therefore, this is also a variable coefficient linear term. This is a variable coefficient linear term. This is a linear term. Overall ODE is linear variable coefficient ODE, linear. And the order is the second order. The last one, easy to see. This is no problem, a linear term. This is linear, but this is non-linear. 2y squared, right? So 2y squared can be written as 2y times y. The coefficient of y is 2y, and the coefficient happens to be a function of the dependent variable y. Therefore, this would be non-linear. It's second order ODE because this highest derivative is the second derivative. So by now, you should be able to differentiate between what are linear and what are non-linear ODEs. And from a non-linear ODE, you should be able to write terms that makes the ODE non-linear. There is a standard form of expressing a ODE system. We know that if you have a nth order ordinary differential equation, you can represent it as n first order ODEs. In fact, that is very much required for numerical tools like MATLAB, etc. So even from your chemical, biochemical, environmental engineering principles, if you derive a ODE that is second order or third order or fourth order, you have to convert it into a system of four first order ODEs if your original ODE was fourth order. So converting your ODE, which is possibly of high order, into a system of first order ODEs is very, very important. And we have looked at several examples of that in the past. So I'm not going to go through that again. I would like you to go through the notes and the past video lessons on this idea. Now, when you do convert it into a system of n first order ODEs, let's say you had an nth order ODE, and then you convert it into a system of n first order ODEs, you will get a system like this. So t is the independent variable in this representation. y1, y2, y3, y4, yn are the dependent variables. They are also called the state variables. You can call them state variables, or you can just call them as dependent variables. T is the independent variable. And the right hand sides are different functions, and the functions are dependent on the dependent variables. They may be functions of the independent variable as well. So f1, f2, fn are the right hand sides of the functions that represent the ODE in standard form. Now we know in order to solve an nth order ordinary differential equation, whether you represent it as an nth order ordinary differential equation or n first order ordinary differential equation system, you require n conditions to solve the problem. And if the n conditions are given at the same value of the independent variable, then it becomes an initial value problem. If some of the n conditions are given at one value of the independent variable and the remaining of the conditions are made known to us at another value of the independent variable, that becomes a boundary value problem. We have already gotten introduced to these kinds of things earlier. So this segment focuses on initial value problems. Therefore, we assume that the values of all the state variables or all the dependent variables y1, y2, yn are known at time t is equal to 0. And the values are specifically C0, C1, C2 all the way till Cn minus 1. So what is shown here is one way of writing it. It may also be denoted in some text as y1 at t is equal to 0 is C0, where C0 is a number. Sometimes they write it as y2 at t is equal to 0 is c1, etc. So there are different ways of stating it, but all initial value problems should have all the state variables or dependent variables given at the starting time. And the starting time, we typically take it to be time t is equal to 0. So if x was the independent variable, and let's say we are talking about a reactor, so x is equal to 0 is the inlet and x is equal to L is the outlet. So here the concentration C is the dependent variable and x, the position along the length of the reactor, is the independent variable. So we have to be given the conditions required to solve the problem at x is equal to 0 at the reactor entrance so that we can compute the concentrations at any point inside the reactor and at the exit of the reactor. Or you must be given all the conditions required to solve the problem at some other point in the reactor. It could be somewhere in the middle of the reactor or at the end of the reactor. But the conditions should be given all at the same values of the independent variable. That is what makes it a IVP. Given this standard form, our goal is to find out the values of y1, y2, y3, y4, yn as a function of time. So we are given the conditions at time t is equal to 0. The state of the system is known. But once we leave that base 0, we want to know what are the values of y1, y2, y3, yn until a final time. Let's call that as tf. So the domain of interest for us is, in this particular case, with t as the independent variable, it's from 0 to tf. We would like to know the state of the system until the final time tf. We know the conditions at t is equal to 0. Therefore, I'm not putting it as 0 less than or equal to t, right? Because we know everything at t is equal to 0. So we have to go from 0 plus, right? So I'm going to just leave it as 0 less than t less than or equal to tf. So this will be the goal in what we are going to do. And as stated earlier, we are going to look at Taylor series expansion and we are going to look at some finite difference approximations, both of which have been introduced to us already. I'll stop here and catch up with you in the next video. Thanks for your time.